Mm, okay. Hmm. So last class we seen this uh, atomic structure, Bohr's atomic model, and how the electrons are there, and what is how the electron and how the electrons are moving around the nucleus. In nucleus, what will be there? What are all those we discussed in the last class? No? Yes. Okay. Today we'll discuss about and we also seen this classification of semiconductors like those are classified into conductors, semiconductors, and insulators. So if you are associating with only one atom, then we call as energy levels. Okay, here we have seen energy levels. If you are associated with a group of atoms, suppose some lakhs of or some millions of atoms are there, silicon atoms are there, we call as energy bands. Okay, energy bands, and whatever the free electrons means the outermost electrons present we call as valence band, and the freely available electrons present are nothing but conduction band. If you apply any external supply or external heat, the electron will excite from valence band to conduction band. So when the electron is associated with this valence band, then that is associated with the atomic structure. And when an electron is present in the conduction band, this is nowhere associated with the atomic structure, and electron will be not available in the forbidden energy gap. Okay, that we have seen. And what is valence band, conduction band, forbidden energy gap, that we have seen. And at 0 Kelvin, silicon is acting as the insulator, but at 300 Kelvin, at room temperature, what happens? This will breaks the covalent bond, and it will makes free, and it will jump from valence band to conduction band. So that means how many, suppose here one electron, so it will acquire energy. Some electron will acquire energy and it will jump from valence band to conduction band. So here electron is forming. So how many number of electrons are forming? That many number of holes are forming in the valence band. That we can say. And next, as in the conduction band, there is no forbidden energy gap, and conductivity is more, and resistivity is less, like copper and aluminum. And insulator have more forbidden energy gap. So this much of energy is required to jump the electron from valence band to conduction band, like mica, wood. So this is having low conductivity and high resistivity. And semiconductor have moderate conductivity, like from 10 power 4 to 10 power minus 6 per ohm meter, and moderate resistivity 10 power minus 4 to 10 power 6 ohm meter, silicon and germanium. These are the semiconductors. Okay. Like this is the atomic structure for silicon and germanium. If you see, silicon have the valency of how much? So silicon has the valency of 4. So in first K shell you have 2 electrons, okay, and L shell you have 8 electrons, and M shell you have 4 electrons, okay. And for the germanium, for the K shell you have 2 electrons, L shell you have 8 electrons, M shell you have 18 electrons, okay. Atomic number is 32 for the germanium, and for element N shell, okay, N shell you have 4 electrons, okay. N shell you have 4 electrons, okay. This is about the silicon, okay. I'm audible. Your response. Hello. Yes.
Yes, sir.
Okay. Next you see. So next, why we are reason for silicon over germanium. So before 1947, they used the germanium only. Okay, germanium for making this semiconductors. But after they are using means we need to use our ICs with different climatical conditions. So this germanium can withstand up to 1000 degrees Celsius only. This is unstable with the high temperatures. And as we already seen, as electrons are moving away from the nucleus, so here 4 electrons are available in N shell. Energy will increase. Okay, here silicon 4 electrons are available in the that means in the M shell. So that means 4 electrons will be tightly bound in the silicon, whereas for germanium, 4 electrons are loosely bound with the silicon. So this is unstable with the temperature. Okay, and next, what they realized means germanium is not that much uh, good material for our semiconductor, and they realized that silicon is a good material, and so what they so and also so by means there are so many techniques came for purification of silicon, and so many techniques are came, and this is abundantly available, and silicon is stable material. It can withstand up to 150 degrees Celsius. Okay, so it withstand up to 150 degrees Celsius. So in cold condition also it can withstand. So we are using our VLSI ICs with different climatical condition. Okay, and it is abundantly available in the earth crust. Around 24% of silicon is available in the earth crust. That's why silicon is a good material for our making our VLSI ICs. Okay, then the germanium. Okay, so this is about basically, if you see this energy forbidden energy gap also for the silicon, this is the 1.1 electron volt. For germanium, this is 0.7 electron volt only. Okay, so means it is unstable. Okay, with certain temperature, it is unstable. Okay, that is the reason why silicon over the germanium in the semiconductors. Okay, silicon is widely used in the material. Okay, so energy bands in the silicon, so that I told you now. So if you see the energy bands, energy gap, so atomic number is how much silicon atomic number is 14. So it is available in the M shell, whereas germanium, it is available in the N shell. Okay. So energy is, last class I told you there are two types of energies are available, like kinetic energy and potential energy. As the electron is moving away from the nucleus, the energy will increase. It is easy to remove 4 electrons from the N shell, and it is difficult to remove the 4 electrons from the M shell. Okay, so that is the main reason. These are the reasons. Okay, and next, so these are the energy levels. Suppose if you see TC the silicon, silicon have energy. That means here, like this is having the atomic weight 14. No, 14 means here energy level 2 and 8. Okay, these are already stable condition. We can't do anything. Okay, and if you see this one, what is the energy level like from E3 minus, if you write E3 minus E4, how much is the energy level? That means 1.1 electron volt you are getting. Okay. So that is the valence band. So valence band is 1.1 electron volt you are getting. That means the gap between valence band and conduction band is 1.1 electron volt. Okay. And so that what here there is a, suppose you have energy level zero point 0.7, and so 1.8 minus zero point 0.7 is how much? Around 1.1 electron volt. Okay, so till now any doubts in this? Shall I move forward? Give response so that I will move forward.
Yes,
Yes.
sir.
Okay. Next you
Yes.
see. Yeah. Semiconductors, there are two types of semiconductors are there. One is intrinsic semiconductor, and we call as what? Pure type of semiconductor. Okay. So semiconductors are intrinsic semiconductor. Okay. Intrinsic semiconductor are pure semiconductors. Okay. Mm. Next is extrinsic semiconductor. Extrinsic semiconductors are nothing but impurities. Okay. Impure semiconductors. So as I told you, silicon at 0 Kelvin, this is acting as what? Insulator. Insulator. Okay. At 300 Kelvin, at 300 Kelvin, what happens? 300 Kelvin means what? 273 degrees Celsius plus 273. 273, if you add, you will get 300 Kelvin at room temperature. This is nothing but room temperature. At room temperature, what happens? This makes one, this is pure silicon. This makes one covalent bond. This is nothing but covalent bond. Okay. So what happens? This electron is there now. So this electron, what this electron will
Sir, your
do?
voice.
One second.
Sir,
Yeah,
your
my
voice is
voice is
breaking, sir.
okay. Now is it fine? Yeah. Please tell me
Yes, sir.
now. Okay. Yes. So here this electron will this electron will acquire some energy, and it will jump, it will break this covalent bond, and it will make free. That means it will jump from valence band to conduction band. Okay, so that means how many number of electrons are jumping from valence band to conduction band, that many number of holes are available. Suppose here one electron is there, an electron is there. So it is here, this is valence band. So it is jumping to conduction band means here one vacant position is happening. Okay. So vacant position is happening means what? Here one hole is forming. Hole is nothing but practically hole will not exist. Just what we call absence of electron is nothing but hole. Okay. So if you see the intrinsic semiconductor, it is pure semiconductor, and it has lower conductivity. I told you, at 300 Kelvin, it is acting as a conductor. So it is having the lower conductivity compared to extrinsic semiconductor. So at 0 Kelvin, there is no free electrons are available. Okay? Free charge carriers are available. It has a, one second. Mm, yes, one second. Just check. Okay. Yeah, now my voice is clear, no? Your response? Hello. Hello.
Yes,
Yes.
yes.
Yes, sir.
Okay, okay. Now you see. So it has equal number of electrons and holes. So that means I told you, like equal number of electrons and holes means so when it will acquire some kinetic energy, that means during room temperature, the number of electrons jumping from valence band to conduction band. That how many number of electrons are jumping, that many number of holes are forming. That means in pure semiconductor we can say that number of electrons, number of free electrons and holes are equal. There are equal number of free electrons and holes. Okay, and it is having negative temperature coefficient. What is negative temperature coefficient? That means as the temperature increases, resistance decreases. Okay, so the conductivity increases. No, so as the negative positive temperature coefficient means as the temperature increases, resistance increases. But our semiconductor having the positive temperature, negative temperature coefficient. Negative temperature coefficient means as the temperature increases, resistance decreases. Man, that means the conductivity. What is difference between conductivity and conductance and resistance? So as conductance, so you can write conductance equal to what? 1 by resistance. Okay. So as resistance decreases, conductance increases. Okay. Resistance decreases, conductance increases. So that means we can say that it is having negative temperature coefficient. Okay. Is it find the points related to intrinsic semiconductor? Yes. Give response so that I will move forward.
Yes, sir.
Now, extrinsic semiconductor. Extrinsic semiconductor is nothing but what? Like we need to add some in a periodic table. Like last class I told you, like this is having the group four elements. Okay, and you have group five elements and group three elements. Okay, so if you need to add some impurities. Okay, so you need to add some impurities. That is nothing but doping. Doping is nothing but adding the impurities to the pure semiconductor. That is nothing but doping. Okay, suppose if you are doping with the pentavalent impurities. What are the pentavalent impurities? You can remember like this. PAB means what? Phosphorus, arsenic, antimony, and bismuth. Okay, so phosphorus, arsenic, antimony, bismuth, you will get a extensive semiconductor, that is n-type semiconductor. Okay, when you dope with so the majority carriers are electrons. Okay, and here p-type semiconductor. P-type semiconductor means you need to dope with this is pentavalent. Pentavalent means 5, and here trivalent impurity. Trivalent impurities means you need to dope with you can remember like this Baji. Baji means boron, aluminum, gallium, and indium. Okay, boron, aluminum, gallium, and indium. This is having the valency of 3, and pentavalent impurities have the valency of 5. Okay, so the p-type material you get, the majority carriers are holes. What are the majority carriers? Holes. Okay. So extrinsic semiconductor. Okay. So impurities with the pure semiconductor make the extrinsic semiconductor. Okay. So due to impurities, it is having the higher conductivity. I told you, no, like at room temperature, pure semiconductor will act as conductor only, but low conductivity will be there. Okay, that is not sufficient for using this as semiconductor. So we need to add some more impurity to make increase the conductivity. Okay, it has higher conductivity. So impurities will define the number of free electrons and holes. Okay. Basically, impurities are added in units of parts per million. Parts per million means suppose like if you are adding one suppose 100 one parts per million. So one part per million means in 1 million 1 million is what, how many lakhs? 10 lakhs. 1 million means what? 10. No? So in 1 million, we are adding one uh, phosphorus atom that we call as one parts per million. So impurity is defined in terms of what? Parts per million. Okay. Suppose if I call 100 parts per million, 100 parts per million means what? In 1 million silicon atoms, we are adding 100 like boron atoms. Okay. We are getting p-type material. Okay. Impurities are added in terms of what? Parts per million. So example, you have n-type and p-type material. N-type and p-type material. Okay. This is about intrinsic and extrinsic semiconductor. Is it fine? Shall I move forward? Yes. Hello.
Yes, sir.
Yeah. Next you see. So if you see this one, uh, so one second. Yeah. So there are N-type semiconductor and P-type semiconductor. See here. Here you have a silicon atom. Silicon atom is replaced with phosphorus atom. Okay. So phosphorus atom have how many valence electrons? Five valence electrons. Okay. So that means here this four valence electrons will share by this silicon atom. Four valence electrons will be shared by the silicon atom. And here what happens? One free electron will be formed. This is nothing but free electron. Okay. So that means how many number of phosphorus atoms you are adding, that many number of free electrons will be formed. Suppose if you are adding 100 phosphorus atoms, 100 free electrons will be formed. 1000 phosphorus atoms, 1000 free electrons will be formed. Okay. So like this is responsible for conduction. This electron will be responsible for conduction when it should jump from where to where? Valence band to conduction band. Okay. So do you understood? Yes. See here. In N-type semiconductor, we add what? Pentavalent impurities. What are pentavalent impurities? Those are 5 electrons in the outermost orbit. Okay, those are pentavalent impurities. Basically, we are using means what? Phosphorus, arsenic, antimony, and bismuth. Okay, and next, with impurity, one free electron is added. So with every impurity, one free electron is added. Okay. This is nothing but what? This is also called as donor impurity. Donor impurity is nothing but what? It is donating the electron. Means this impurity we call as what? One free electron it is donating. Suppose like donors, who are the donors? Suppose in the blood, who are giving the blood? Those we call as donor. No, so they will give the blood for that. So here like that, who are having excess of amount, they will give donation to some other orphanage like that. No, so here this impurity having excess of electron. That's we call as donor impurity. Okay. So what are the impurities? Phosphorus, arsenic, antimony, and bismuth. Okay. So in this N type, what are majority carriers? Majority carriers are electrons and minority carriers are holes. Okay. So do you understood about this N type semiconductor? Shall I move forward? Yes. Now you see p-type semiconductor. What is p-type semiconductor? So initially we see in the atomic structure for silicon. No? Atomic structure for pure silicon. Where is atomic structure of pure silicon? Somewhere we have seen the atomic structure of pure silica. So last class we have seen, okay, covalent bond, sharing of electron. So here silicon atom is replaced with what? Aluminum atom. I told you, pentavalent impurities. What are the pentavalent impurities? Bargene. Bargene is what? Boron, aluminum, gallium, and indium. Okay. So these are the pentavalent impurities. Okay. Okay. What happened? Okay. So what are the pentavalent impurities? P-type semiconductor material. We add trivalent impurities. What are the trivalent impurities? Those are having 3 electrons in the outermost orbit. Those are trivalent impurities. With every impurity, one free electron will be added. Okay. This is also known as what? Acceptor impurity. Why it is called acceptor impurity? It is accepting the electron. Okay. That means it want to accept the electron. That's why we call as acceptor impurity. Like the boron, aluminum, third group, which are having in the third group, boron, aluminum, gallium, and indium. Those are the trivalent impurities. In this p type, the majority carriers are holes and the minority carriers are electrons. Okay. So this is about p type semiconductor. Yes. Any doubt in this? Give response. P type and N type semiconductor. What are N type semiconductor? What are P type semiconductor? Okay.
Yes.
Okay. Next, if you see, next if you see, there are two currents in the semiconductor. One is diffusion current, and next one is drift current. Okay. So what is the diffusion current and drift current? We'll see. Okay. There are two currents in the semiconductor. Okay. So one is drift current, and next one is diffusion current. Diffusion current. Okay. So what are these currents? We'll see. Okay. So drift current, before that we will see drift velocity. So what is this drift velocity mean? Suppose one hole is there. One hole is there. So hole, before applying some electric field, this is the trajectory. This black color is there, no? Black color. This is the trajectory. Okay. This is the final position of hole. Okay. After applying the electric field, this brown color is there, no? So this is the trajectory. Okay. Motion of this hole. So there is a difference in this trajectory, no? There is a difference in this trajectory. Okay. So there is a difference. So we can say that this is due to what? Drift velocity. This is nothing but Vd. So Vd is nothing but what? Velocity of charge carrier due to velocity of the charge carrier due to external electric field. So Vd is given by what? Mu into E. Vd is nothing but drift velocity, and mu is nothing but mobility of charge carrier, and E is nothing but applied electric field. Okay. So this you need to remember. So Vd equal to what? Mu into E. So mu is nothing but mobility of charge carrier. Here what is this mobility of pole? There should be some mobility, no? It is moving with some velocity. That is nothing but we call as mobility, and E is the electric field. Okay. This is about the drift velocity. Okay. Did you understand what is drift velocity? Shall I move forward? Hello. Yes.
So can you
Okay.
explain again?
Okay. Okay. See here, there are, so basically there are two currents are there. One is a drift current and diffusion current. Okay. So before drift current, I want to explain about the drift velocity. Okay. So drift velocity is nothing but suppose one hole is there. One hole is there. Okay. So this hole is randomly moving. So like this is the trajectory. Okay. So this is the trajectory. Randomly it is moving and it is coming to the final state. Okay. So this is nothing but without applying some external electric field. Okay. And after applying external electric, this is without applying external electric field. When you apply some external electric field, okay. Suppose for hole, you are applying some negative voltage. Due to this negative voltage, what happens? No, positive voltage you are applying. Positive voltage means what? Hole have positive charge. This will repel. No? So externally you are applying some voltage. So you are applying some voltage means what happens? It will change its trajectory and it will move like this, and it will come to the final state here. Okay, so this final state is here and this final state is here. So what happens? There is a change in the trajectory now. At final state, there is a change in the trajectory. This is nothing but what? Before applying external electric field. This is nothing but after applying external electric field. Okay, so that is nothing but we call as a drift velocity. We call as drift velocity. So what is drift velocity? The velocity of charge carrier due to external electric field is nothing but it will changing its velocity. Actually, at the final position and changing its final position. This is before applying external electric field. This is after applying external field. Those are not same. Okay, there is some difference. There is nothing but drift velocity. So it is given by what? Mu into E, where mu is nothing but mobility of charge carrier and E is nothing but applied electric field. So Vd equal to what? Mu into E. This is the formula. Okay. Okay.
Yes, sir.
Okay. Next you see. So what happens? We are talking about drift velocity, drift current, no? So drift current means suppose like here you are applying positive voltage. Okay, 1 second. Here you are applying positive voltage. Okay. Here you are applying positive voltage. Here you are applying negative voltage. So here you are applying positive voltage means let us take these are holes. These are nothing but holes. Okay. Holes have which charge? Positive charge. No? Next you have electrons. Electrons have which charge? Negative charge. Okay. So there are two types of currents are there. Suppose holes are moving like this. Okay. Okay. Holes are moving like this. What is the hole current? Same direction. No? What is the hole current? Same as the direction of holes. Okay. And next, some electrons are there. Electrons are moving like this. How is the electron current? This is the movement of electron. The electron current is opposite to the direction of the electron. Okay. So this is the electron current. Okay. So this is nothing but electron current that we call as what? Conventional current. Okay. So you need to understand about the currents very well in this. Okay. 1 second. Yeah. So yeah, if you see, yeah. So what happens? You are applying positive charge. You are applying positive charge. What happens? Electrons will be attracted toward this positive charge, and holes will be repelled toward this negative charge. Okay. So what happens? So current due to electrons is from where? Electrons are moving from this negative to positive. Okay, electron current will be opposite to the direction of the electrons, so that means this is due to electron current. And however hole current, that is same as the direction of holes. Let us take the hole current is H. Okay, due to this applied electric field, there is current is there. Okay, so if you apply KCL, you know current law. What is Kirchhoff current law? In networks you studied KCL, Kirchhoff current law. Entering current equal to leaving current, no? So that means here I equal to what I can write as what I can write IE plus IH. KCL is satisfying, no? Entering current equal to leaving current. Okay. So this is nothing but Coulomb's law. Coulomb's law is nothing but what? When external electric field is applied to the semiconductor, holes experiences force in the direction of electric field, and electrons experiences the force in the opposite to the direction of electric field. Here you are applying the electric field. Okay, you are applying some electric field. Okay, electric field. So the electric field is from where to where? Positive to negative. Okay, so normally electric field is nothing but we can call as dv by dx. Okay, applied electric field with respect to we can call as the distance. With respect to distance we call as electric field. How the electric field applying from positive to negative? So holes experiences electric field with respect to what? With respect to electric field in the same direction. Electrons will be exhibit electric field opposite to the direction of electric field. So from this you can say that F equal to what? Q into E. F equal to what? Q into E, where Q is the charge and E is the electric field, and F is nothing but force. Force applied. Force applied equal to what? So that is equal to Q into E. So this is a semiconductor material under external electric field. Okay, external electric field. Yeah, is it fine? Give response. Yes.
Yes,
Shall I
sir.
move forward? Okay. Next you see. So if you see the drift current, drift current. So current. So what is drift current? Drift current is nothing but it is the flow of electric current due to motion of charge carriers. Motion of charge carriers and applying external electric field. Okay. So here if you see, if you applied external voltage, there will be an electric field. Okay, due to this electric field there is a motion of charge carriers. No, here what are the charge carriers? Electrons and holes are the charge carriers. Okay, so drift current is due to what? Motion of charge carriers due to applied electric field. So I equal to what? This is the formula, NEA into VD. Okay, so I'm not interested about current. I'm interested about current density. So what is current density? Current per unit area is nothing but current density. Okay. So I by A equal to what? NE into VD. I by A I can write as current density, that is J. J equal to NE into VD. Previously you got VD, no? What is VD? Previously you got VD. What is VD? Drift velocity. Mu into E, no? Previously you got VD. VD equal to mu into E. Okay. So J equal to what? NE Q into mu into E. This is the current density. Okay. So N is nothing but charge carrier concentration, and area A is the area of cross section, and J is the current density. Jn equal to what? NQ mu n into E. Jp equal to PQ mu P. Jn is nothing but current density due to electrons. Jp is nothing but current density due to holes. Okay. So NQ mu n into E, PQ mu P into E, where N is nothing but electron concentration, P is nothing but hole concentration, Q is the charge of the electron, and mu N is nothing but mobility of the electron, and mu P is nothing but mobility of hole, and E is the nothing but electric field. Okay. So total current. What is the total current? So total current I can write as what? J equal to JP JN J, total current density. Okay, so this is equal to what I can write? NQ mu n into E plus PQ mu P into E. PQ mu P into E. Okay, so if you take Q and E common, what you are getting? N mu n plus P mu P into Q into E. Q into E. So this I can consider as sigma. Okay, so sigma equal to what? Sigma equal to n mu n plus p mu p. P mu p. So J equal to I can write as sigma into E, where sigma is nothing but conductivity. Sigma is nothing but conductivity. Okay, conductivity. Sigma and this resistivity are reciprocal. Okay, so from this I can write uh, resistivity. 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 I can write as 1 by sigma. So this is 1 by n mu n plus p mu p. This is resistivity. Okay. So current density equal to what? Nq mu n into A plus Pq mu p into E. So if you take common, Nq mu n plus Pq mu p into Q, that is equal to sigma into Q. This is into Q into Q. That is sigma. Sigma into E. Sigma is nothing but conductivity. This is the current due to what? Applying external electric field. Okay, applying external electric field. Yeah, any doubt in this? Give response so that I will move forward. Drift current. Hello, hello. Okay, 1 second. Now my voice is clear. 1 second.
Yes, yes.
1 second. 1 second.